All right, so we're going to look at how to find and interpret p-values. We'll look at how to use p-values for a z-test for a mean when the standard deviation is known. We'll look at how to find critical values and rejection regions in the standard normal distribution. And we'll look at how to use rejection regions for a z-test for a mean when the standard deviation is known. Okay, so to use a p-value to make a conclusion in a hypothesis test, we want to compare the p-value with alpha. And we talk about this in 7.1, but this is kind of the foundation for what we're doing here. So I want to emphasize it again. When p is less than or equal to alpha, you're going to reject H sub O. And then when p is greater than alpha, you're going to fail to reject H sub O. And remember, alpha is your level of significance. So here's how we will apply that. In this first example, the p-value for a hypothesis test is p equals 0.0237. What is your decision if the level of significance is alpha equals 0.05? So we're going to compare p and alpha. P was 0.0237, alpha is 0.05, so p is less than alpha. So that means we should reject the null hypothesis. Okay, what if alpha is 0.01? Okay, if alpha is 0.01, then we're going to compare the given p-value 0.0237 and 0.01. This time p is greater than alpha. So like we said on the previous slide, when p is greater than alpha, we fail to reject the H sub O. Okay, so how do we find the p-value if it's not given? Well, after determining the hypothesis test standardized test statistic and the test statistics corresponding area, we need to do one of the following to find the p-value. If it's a left tail test, then P is going to be the area in the left tail. If it's a right tail test, then P will be the area in the right tail. And then if it's a two-tail test, then P is going to be 2 times the area in the tail of the standardized test statistic.
And the left tail was less than and the right tail greater than, right?
Yes.
Okay.
And the two-tailed was the not equal to part.
Yeah.
Okay, so here we want to find the p-value in this example for a left-tailed test, a left-tailed hypothesis test with the test statistic of z equals negative 2.23, and we want to determine whether to reject H sub O when the level of significance is alpha equals 0.01. So if it's a left tail test and our z value is negative 2.23, this is what the graph looks like. And so basically we need to find the area of this blue part. So in order to find the area of that, we're going to use our calculator and do the normal CDF. So this is something we did back in one of the previous sections. Let me pull my calculator up here. There we go. Okay, so normal CDF, we're going to go to second vars and then number 2. Our lower bound is negative infinity, so you can write negative 10,000, or if it defaults to negative 1e99, that's fine. Your upper bound is negative 2.23 from the z-score, and then standard deviation is 1, mean is 0. Set those backwards there, but mean is 0, standard deviation is 1. And so that's where we get the 0.0129. So that p-value of 0.0129, when I compare that to my level of significance given to be 0.01, right? then it's greater than. So when it's greater than, then you fail to reject H sub 0.
You make sense so far. Don't get crazy.
Okay, next. Make sure I didn't go too many slides. There we go. This time we want to find the p-value for a two-tailed hypothesis test with a test statistic of z equals 2.14. We want to decide whether to reject H sub 0 when the level of significance is alpha equals 0.05. So this time when we have a two-tailed test, our p-value is going to be 2 times the area in the tail of the standardized test statistic. So 2.14 is over here on the right since it's positive. So to find this area here, 2.14 is our minimum this time. And so our maximum will be infinity or 10,000 or 1E99. And then we still use 0 for the mean and 1 for the standard deviation. So when you put that in your calculator, you should get an area of 0.0162. But now remember, this is a two-tailed test, so I have to multiply that by 2 before I compare it to my alpha value of 0.05. So 2 times 0.0162 is 0.0324. And when I compare that to 0.05, it's less than. So when it's less than, then we reject H sub 0.
On two-tailed, we put the first number in.
Well, the only reason we put the first one in this time is because my z-score is positive. So that tells me it's over here. So when you look at that blue area, this is now your minimum. If they'd given you your z-score of negative 2.14, then that would be fine in the area here, which would be the same thing. And then you could do negative infinity and your maximum being negative 2.14. But just since they gave me a positive, it was easiest to find this area. And so that makes my minimum. If you're looking at this side, your minimum is negative infinity and your maximum is that value. They didn't give me this side. We could assume what it is. So if you really don't want to change that, you could do negative infinity to negative 2.14 and you should still get the same area because this is symmetrical. So those areas are the same. Okay. So if it's right-tailed or if it's two-tailed and they give you the positive, then that's when you're going to know that the z-score is your lower bound and then it goes to infinity. When it's left-tailed or two-tailed and they give you a negative, then you'll be looking at negative infinity to that number. So that's why the graph is kind of important because when you see it on the graph, you can kind of see your maximum and your minimum a little better then.
Then we times it by that number.
And then you multiply it by 2 because there's 2 blue areas and we just found this one over here. And so if we want to find the total, we multiply it by 2 because these are symmetrical. So they'll always be the same on each side. Those areas will be. And so now I'm comparing that to my 0.05. And since it's less than, we reject. Okay. Okay, so the z-test for a mean. The z-test for a mean is a statistical test for a population mean. We've seen this score or this formula before, but just to remind you, the test statistic is the sample mean X. The standardized test statistic is Z. Z is equal to X bar minus the mean. And you're going to divide that by the standard deviation over the square root of n. N is your sample size. So that is your z-test when the sample is random, at least one of the following is true. Either the population is normally distributed or n is greater than or equal to 30. Okay, so the next 2 slides are kind of a chart laying out the steps that we've just talked about, kind of summarizing everything. So when we're using p-values for a z-test for the mean, the first thing you want to do is verify that the standard deviation is known. the sample is random, and either the population is normally distributed or n is greater than or equal to 30. Once you've verified that, then we're going to state the claim mathematically and verbally. So this is where you identify H sub O and H sub A. And then you will specify the level of significance. So that's your alpha. And then you'll find the standardized test statistics. So that's the formula we just talked about for Z. And you want to find the area that corresponds to Z. So this is where you can use your Z-score chart, but we've pretty much been using the TI-84. So that's probably what you're more comfortable with. So use your graphing calculator. That's where we did the normal CDF. So I put a little note there beside it in case you forget which part to use. And then we want to use that to find our p-value. And then remember, if it's left-tailed, then P is the area in the left tail. When it's right-tailed, P is the area in the right tail. And when it's two-tailed, bless you, you're going to take P as the value of 2 times the area that you find. And then you'll make a decision to reject or fail you'll make a decision to reject or fail to reject the null hypothesis. So this is where you compare your P and your alpha. If P is less than or equal to alpha, then you reject H sub O. Otherwise, you're going to fail to reject H sub O. And then you'll use what you did in part 7 to interpret the decision in the context of the original claim. Okay, so let's put all of that together and look at an example. So example 4 says that in auto racing, a pit stop is where a racing vehicle stops for new tires, fuel, repairs, and other mechanical adjustments. The efficiency of a pit crew that makes these adjustments can affect the outcome of a race. A pit crew claims that its mean pit stop is less than 13 seconds. A random sample of 32 pit stop times has a sample mean of 12.9 seconds. We want to assume the population standard deviation is 0.19 seconds. Is there enough evidence to support the claim at alpha equals 0.01? Okay, so I'm going to kind of start. What I would do would be write down on my paper all of these values that they give me, what is what. So this is telling me that the mean is less than 13. Okay. And then a random sample of 32, that tells me N is 32. Then we have a sample mean of 12.9. That's going to be, sample mean is your X bar. And we want to assume the population standard deviation. So my standard deviation is 0.19. And then I have this alpha value of 0.01. So as you read through a problem like this, that would be the first thing I would do on my paper is write down what all of the numbers, what variable those values represents. Okay, it did tell me that the sample is random, and then our N value is more than 30 anyway, so we know we can use the Z-test. We want to name our H sub O and H sub A, and most of these problems seem to kind of do step-by-step for you. So the first thing that would pop up on my lab is for you to pick the H sub O and H sub A. We had back here that our mean was less than 13, so that's going to be my H sub A, leaving H sub O to be the complement. The mean is greater than or equal to 13. Okay, so now I need to find my standardized test statistic, which is Z. And so here's where I use my formula. X bar was 12.9. I subtract 13 from it. So this number that is in your statement, that is going to be what you're going to use for your mean. And then your standard deviation was given to be 0.19, and you're going to divide that by the square root of 32. When you put that in your calculator, you get about negative 2.98. Okay, so that means that, first of all, when I look back here at my H sub A, it's less than, so I know I'm going to be using a left-tailed test. And so this is what it would look like on the graph. Okay, so this little blue part is what I want to find the area of. And so we're going to put this in our calculator, normal CDF. And then since this is a left-tailed test, there's no bound on the left. So your lower limit, your minimum is negative 1E99, but then the maximum is that Z-score you found, negative 2.98. And then you've got mean of 0, standard deviation of 1. That gives you 0.0014.
Can you go back one slide?
Mm-hmm. Okay. Okay, so when I compare that 0.0014 with my 0.01, P is less than alpha. So that means I reject the null hypothesis. All right, so for this particular problem, your statement would be that there is enough evidence at the 1% level of significance to support the claim that the mean pit stop time is less than 13 seconds. All right, let's look at another one. According to a study of U.S. homes that use heating equipment, the mean outdoor temperature at night during winter is 68.3. So that's the first thing I'm going to make a note of. That is, so my mean means equals 68.3. If you think this information is incorrect, you randomly select 25 U.S. homes. So my N is 25 that use heating equipment in the winter, and you find that the mean outdoor temperature at night is 67.2. So that means my X bar is 67.2. From past studies, the population standard deviation is known to be 3.5 degrees Fahrenheit. So there's my standard deviation. And the population is normally distributed. So those are the keywords I need to proceed to be able to find my Z-score. And then is there enough evidence to support your claim at alpha equals 0.05? Okay, so our claim is we've got the mean is 68.3. So we're going to say the mean, H sub O is the mean is 68.3, and H sub A would be the mean is not 68.3. And so now we need to find our Z value. And so I'm going to take the X bar, which we said was 67.2. I'm going to subtract my mean, which is 68.3. I'm going to divide by my standard deviation of 3.5 over the square root of 25. That gives me negative 1.57. Everybody okay with putting this in your calculator? Anybody want me to do that with you? I would use my fraction button, and then for the denominator, you could do the fraction button or the division button there. Okay, so since this time my Z value is negative 1.57, here's what we've got. And so since it's a negative, that's the tail that I'm going to be finding the area of. But then it's two-tailed, so I need to multiply by 2. So since this is the tail that I'm putting in the calculator to find the area of, then this time, since it's to the left, then there's no bound on the left, but my upper bound is the negative 1.57. So put that in your calculator, you end up with 0.0582. And so I multiply that by 2 to get a p-score of 0.1164. So now when I compare that to my level of significance of 0.05, P this time is greater than alpha, and so L to reject the null hypothesis. So as far as this problem goes, this means there is not enough evidence at the 5% level of significance to support the claim that the mean indoor temperature at night during winter is different from 68.3 degrees Fahrenheit for U.S. homes that use heating equipment. Okay, you can also use your graphing calculator to help you find the p-value. You have something called the z-test, okay, and we'll look at an example to go through this again here in a minute, but just in looking at this, you can see that when you put it in your calculator and you do the z-test, it gives you a p-value. And so in this particular problem, when you compare the p-value to an alpha of 0.05, then p is less than alpha, and so you can reject the null hypothesis. And we'll look at an example here in a minute where we'll actually go through that screen on the calculator to make sure you know how to use it. Okay, let's talk about the rejection region and critical values. The range of values for which the null hypothesis is not probable is called the rejection region. Sometimes it's referred to as the critical region as well. If a standardized test statistic falls in this region, then the null hypothesis is rejected. A critical value, z sub 0, separates the rejection region from the non-rejection region. So when we want to find the critical values in a normal distribution, we want to specify the level of significance alpha. We want to decide whether the test is left, right, or two-tailed. We want to find the critical value, which is our z-score. When the hypothesis test is left-tailed, the z-score that corresponds to an area, we want to find the z-score that corresponds to an area of alpha. When it's right-tailed, we want to find the z-score that corresponds to an area of 1 minus alpha. And when it's two-tailed, we want to find the z-score that corresponds to 1/2 alpha and 1 minus 1/2 alpha. So here's what that looks like. We will sketch the standard normal distribution and draw a vertical line at each critical region and shade the rejection regions. So the left-tailed test looks like this one, right-tailed test looks like this, two-tailed test looks like what we have here. Okay. And then the rejection regions are the shaded parts or the blue parts. Okay. So for this one, we want to find the critical value in the rejection region for a left-tailed test with an alpha value of 0.01. So if our alpha value is 0.01, this is what it looks like. And so if we want to find the z-score, then we're going to use inverse norm of that alpha value, because that's our area, and then 0 is our mean and 1 is our standard deviation. So this time we are finding the z-score given the area. Where the problems we looked at before, we were finding the area. So that tells me that I have a z-score of negative 2.33. And then Mo and any others who like to use Excel, this is how you put that in Excel to get your negative 2.33. Okay, let's look at how to find it for a two-tailed test. When we want to find the critical value and rejection region for a two-tailed test with alpha equal to 0.05, we're saying that the blue areas are our rejection region and they have a total of 0.05. So that means that we have 0.025 on each side. So when we want to find the z-scores, we're going to use 0.025 and then 0.975, because you remember when we put this in our calculator, it's assuming you're looking at to the left. And so if this part is 0.025, then to the left of it would be 0.975. So when we want to find those z-scores, you're going to use inverse norm again. You'll put in 0.02501 to get negative 1.96. And then to get the other one, you're going to use 0.97501 and get positive 1.96. Now, is it necessary to do this second one? I mean, you can figure it out once you have the first one, because you're going to have a positive and negative at the same number because this is symmetrical. So this means that your rejection regions are to the left of negative 1.96 and to the right of positive 1.96. Any questions there?
I have 5 lost on that.
Which one?
I'm lost on that one.
So when you ended up with an alpha of 0.05, then that means the blue areas together have an area of 0.05. So to figure out what each one would be, you divide that in half. So that leaves 0.025 for each one. And so when you want to find the z-score here, when you put that in your calculator, the first thing it asks you for is the area. And so that area for this side is going to be 0.025. And we're saying it's the left tail. And so that gives me my negative 1.96. Okay. When you want to find this z-score, the way it's set up for the z-score, it's always assuming you want the area to the left. So I can't use 0.025 again because I'll still get this same negative number. I would have to use 0.975 for all of this.
Where did you get that left at? See that in my calculator. You have that?
Oh, you don't have to worry about it if it's not there. It's just if it is there, you have to pick something. Okay. Now, once you get the first one, if you know it's two-tailed, you can just change the sign on the other one if you want. Now, here's why these rejection regions are important. If you would like to use a rejection region to conduct the hypothesis, you can find the standardized test statistic Z. And if the standardized test statistic is in the rejection region, then you reject H sub O. And then if it's not in the rejection region, then you fail to reject H sub O. So that just means that if you look at the standardized test statistic, and if it's in this blue part, then you're going to reject H sub O. If it's in this tan colored part, then you would fail to reject it. So here's a kind of summary of how to use rejection regions for a z-test. You're going to verify that the standard deviation is known, the sample is random, and either the population is normally distributed or n is greater than or equal to 30. Then you want to state your H sub O and H sub A. Then you want to find alpha. And you want to find the critical values. So this is where we use inverse norm on our graphing calculator to find our Z scores. Then we want to determine the rejection region based on what we found for step 4. Then you want to find your standardized test statistic, which is our formula for Z, and we'll use that to sketch the sampling distribution, and we want to see if this is in the rejection region. So your rejection region, the boundaries come from your critical values, and then once you look at your standardized test statistic to see if it's in that blue part or the non-blue part, then you use that to decide whether to reject or fail to reject H sub O. If it's in the rejection region, you reject H sub O. If it's not, then you fail to reject. And then you interpret the decision in the context of the original claim. Okay, let's look at an example where we work through all of that. So on this one, employees at a construction and mining company claim that the mean salary of the company's mechanical engineers is less than one of its top competitors, which is $88,200. So we've got the mean is less than 88,200. A random sample of 20, so there's my N, of the company's mechanical engineers has a mean salary of 85,900. So there's my X bar. We want to assume the population standard deviation is 9,500. So there's my standard deviation. And the population is normally distributed. At alpha equals 0.05, we want to test the employee's claim. Okay, so once we figured out what all of our variables stand for, we can write our H sub O and our H sub A. H sub A is our claim, so the mean is less than 88,200, and that makes H sub O, the mean is greater than or equal to 88,200. Then we can find our standardized test statistic by using our formula for Z. X bar was 85,900, the mean was 88,200, so I subtract those and I divide by 9,500 over the square root of 20. That gives me about negative 1.08. Now, I skipped over the Z actual critical value, Z sub 0, to find that based on the H sub A being less than, then I know this is a left tail test. And so I can use inverse norm of 0.0501 to figure out that critical value, which is negative 1.645. So now I want to think about a graph, and that's my boundary on my rejection region. And then I want to see where this score is on that. Is it in the rejection region or is it not? But here's what the graph looks like. There's my boundary at my critical number, negative 1.645. But if I look at where negative 1.8 is, it's not in the rejection region. So since it's not in the rejection region right here, then I fail to reject the null hypothesis. So that means there is not enough evidence at the 5% level of significance to support the employee's claim that the mean salary is less than 88,200. Now, make sure that you understand that this decision made here, even though your sample has a mean of 85,900, you cannot, at a 5% level of significance, to support the claim that the mean of all the mechanical engineer salaries is less than 88,200. The difference between your test statistic and the hypothesized mean is probably just due to a sampling error. Okay, here's another example. This time, a researcher claims that the mean annual cost of raising a child age 2 and under by married couple families is $14,050. So, mean is $14,050. And a random sample of married couple families in the US, the mean annual cost of raising a child is $13,795. So that's my X bar. And the sample N is 500. Assume the population standard is 2,875. So there's my standard deviation. And then we're looking at alpha is equal to 0.10. Is there enough evidence to reject the claim? Okay, so here's my statement. The mean is equal to 14,050. So that's my H sub O, leaving H sub A to be that the mean is not equal to 14,050. So what type of test am I going to have here? Left, right, or two-tailed?
Two-tail.
Yeah, based on that is going to be two-tailed. So this means that when I go to find my z-scores, I have two critical values to find, a positive and a negative. So I'm going to look at the inverse norm of 0.0501. Everybody see where the 0.05 came from? If alpha is 0.10 and this is two-tailed, I had to divide that by 2 to get 0.05. That gives me negative 1.645, and then the other one's going to be positive 1.645. Now, when I find my standardized test statistic, I use my formula for Z. And so I take X bar, which is 13,795. I subtract my mean of 14,050. And I divide by my standard deviation of 2875 over the square root of 500. That gives me negative 1.98. So now I need to look at those two numbers on a graph, and then where is my z-score here, my standardized test statistic. So here is my negative 1.645 and my positive 1.645. And then if I'm looking at my test statistic here, negative 1.98, this time it falls in the shaded region. So that, since Z is in the rejection region, you're going to reject the H sub 0. Now, here's what this would look like on your calculator. If you would rather do that there, you can see it'll find the Z-score for you. But you're still going to have to know, and actually you could use the p-value if you wanted to and not have to use the rejection region. So you're going to go to the z-test, which is under stat test. So if I go to stat and over to test, z-test is number 1. Okay, and this is one where you choose whether or not you have data or statistics. This time, the data is what you're going to choose if it gives you a whole bunch of numbers, like you would be putting it in your list, okay? But this one just gives me statistics, and then I type in my which one are we on again? It's not, yeah, 10, isn't it? So this is going to be 14,050. And then my standard deviation was 2875, and my X bar was 13,795, and my N was 500. This one was two-tailed, so I need to choose that. And then we're not going to worry about the color or anything because we're not going to graph it. We want to calculate. So we're just going to arrow down to where it says calculate. And then I can look at my values here. So this time, since our P is 0.047, I could use that times 2 and compare that to my alpha if I wanted, and not look at the rejection region. But either way, there is enough evidence at the 10% level of significance to reject the claim that the mean annual cost of raising a child by married couple families in the U.S. is $14,050. Okay, so let's have a couple problems for you to try. I actually have 9, 16, and then 21 on the next slide. Now, 21 is a problem where they give you data. So if you're going to use your calculator, you're going to type in your data in L1. So clear out anything you have here, type in your data in L1. And then when you go to stat and over to test and do the z-test, like we just saw in that last example, you'll choose data instead. Okay. And then you'll be able to tell it you put the numbers in L1. Okay, so let's see what we can do on those 3, and then we'll come back together. I think we'll probably have to have a little more discussion on those and make sure we're good to go there. So let's take a few minutes to see what you can do on your own, and then we will get in groups to talk about that if we have time. We're kind of shorter on time today, aren't we? We'll see where we are. Okay, let's get in groups to at least talk about 9 and 16 together, and then we can look at 21 together. I want to make sure you know, remember how to put that data in, okay? So we'll say 1049, we'll say 1053 for groups, and we'll come back out together. Okay, we're 9 and 16, okay? When you get to 21, you're going to need to type this data in on your L1. So I went to Stat, Edit, typed in all of those numbers there. And then when you go to find the critical values in the standardized test statistic, you can go to Stat, over to Test, and do the Z-test. This time you choose that it's data. Your mean was 10 from up here. Your standard deviation was 4 from here. And then this one, your H sub A was less than. So I just made sure I selected that. And then when I calculate there, it gives me my standardized test statistic, that negative 0.47. Then when you want to find the critical value, you're going to go back to second bars and do the inverse norm. This was a left tilt test, so I'm at 0.07 because that was my alpha value. And make sure if you have that option, choose left. And that gives me my negative 1.47. Okay, so that's the boundary on, so actually it should be negative 1.48 if you round correctly, and then this would be my graph. And then when you look at your Z-score, Z is not in the rejection region because of it being negative 0.47, it would be more in this pink part. And so you're going to fail to reject the null hypothesis. Okay, I do have some videos on, let's see, which ones? In the videos folder. Video examples folder that a few people have already asked about, 9, 16, and 21. I just did one video with those 3. So if you need to see any of those, feel free to look at that. And if you need more, just send me a message and I'll be happy to help. Hey, you guys have a great week.